Welcome back. Previously, we've learned two important techniques for counting. One of them is the inclusion-exclusion principle, and the other being the multiplication principle. And both of those are important, and they do help us to count, but there's often some sorts of counting problems that come up where there's a specific technique or a specific tool that we might need. In particular, we've got three different kinds of tasks that we might need to do. We might need to arrange all of the objects that we have. Maybe that's really what our question boils down to. And there is a tool that does that for us. Maybe we are going to select some of the objects we have and then arrange them. Maybe that's our plan, in which case we have a different tool that can be used to help us out. Maybe we're not bothering to arrange things at all. Maybe we're just making a selection. And then for that, we have a third different tool we can use. So we'll look at all three of these tools, one in turn. And then later on in the following section, 3.6, we're going to apply these tools to more complicated counting questions. So let's begin with our first tool. This is the factorial. Factorials are used when we are counting all the possible arrangements. And so a couple of little things to mention here. So when I say all the arrangements, I have to talk about what I'm arranging, and specifically it's a bunch of distinct or different objects. So if I had, for example, 5 different textbooks and I wanted to put them in some sort of an order, a factorial would be totally useful there. If, on the other hand, I had something where there were 3 textbooks that were identical to each other, they were all the same topic, same author, same everything, and another 2 books that were a different topic and a different author, factorials would not be quite as helpful. They wouldn't be able to do all the work for me there. So just to keep that first part in mind, that when I'm using factorial, I've got a bunch of different objects and I'm arranging all of them. What a factorial is, as far as the computation side, it's just a product. So when we're looking at the number of ways to arrange those n objects, that is n factorial, and we write that as n with a little exclamation mark. And what that means is take all the numbers from n down to 1 and multiply them all together. So if I had 5 different books and I wanted to arrange them on a shelf, then I could use factorials to do that, to figure out how many arrangements are possible. 5 times 4 times 3 times 2 times 1. That would be 120. Good news, of course, you don't need to calculate factorials by hand. Your calculator does have a factorial function. On our calculator, the Sharp EL531, if you look right above the number 4, you'll see a little n factorial that's in orange. So you access that with the second function button. So if you wanted to calculate that 5 factorial, you would just enter 5 and then the second function and then 4. And then once you've done that, the little exclamation mark will show up in the display window, and then hit equals and you'll get the answer. So you can practice with this. 7 factorial, if I enter 7 second function 4 in my display window, I'll see a 7 with an exclamation mark. And then once I hit the equal sign, it'll give me my answer of 5,040. There is one little other side note here, which is 0 factorial. It's possible maybe that we have no items, and if we're thinking about how many ways there are to arrange no items, the answer is one way. You just stand there, you don't do anything. That definition for 0 factorial, we really need that because that wouldn't make sense with our original definition that factorials are all the numbers down to 1, because 0 is already less than 1, so how would you go from 0 down to 1? That wouldn't really make sense. So we add on this little side definition for what does 0 factorial mean for us. All right, let's do a couple of examples. Example 1, I've got 4 plants. I'm going to arrange them on my windowsill. So that's 4 distinct things, 4 different things, and they're being arranged in an order. I'm arranging all of them. The answer should be 4 factorial. Which, if we're interested in computing what that is, that's 24. 24 possible options. Sometimes when we're thinking about factorial, even though it's officially for arranging things, maybe the question doesn't mention the word arranging. So in the first part, example one, how many ways are there to arrange them on my windowsill? It was pretty clear we're doing an arrangement. For question two, example two rather, it doesn't mention arranging things. So how do I know that an arrangement is something that makes sense here? I've got 5 different books that I'm giving away to my 5 coworkers. So if you're imagining, here are my 5 books, 1, 2, 3, 4, and 5. And then I've got my coworkers A, B, C, D, and E, and they're all standing in the hallway waiting to come and take their books. If you're thinking about, how might I actually give away these books to these coworkers, I could imagine doing it by taking these coworkers, leaving them in the order that they're currently in, and just arranging my books and arranging whatever order my books need to be in. And whoever is at the top of the line, that'll be the book that I give to person A, and whoever is the second in the arrangement, that's who I'll give to person B. So, for example, if my books had been rearranged so that instead of it being book 1, 2, 3, 4, 5, if my books had been arranged in the order, I don't know, 5, 2, 1, 3, 4, then person A gets book 5, person B gets book 2, person C gets book 1, person D gets book 3, and person E gets book 4. Basically, the idea here is that however I arrange my books, that's one of the different ways I could go around giving out those books to my 5 coworkers. So really, what am I doing? I'm arranging those 5 books in some sort of an order, and that's the order that I'll give them away to coworker A, B, C, D, and E. So 5 books, they're all being arranged. That's 5 factorial, or 120 ways. You could also tackle, for these factorial questions, you could also tackle them with the multiplication principle, just as an aside. Because if we're thinking about doing this very same question, you could choose who's going to get the first book, second book, third book, fourth book, and fifth book. At the beginning, you'd have 5 coworkers, and then once you've given a book to a coworker, they're not getting a second book. So for the second book, you'd have 4 options for how many coworkers, and now you've given away 2 of the 5 books, so you only have 3 books left for the next coworker, and then you'd have 2 books left for the next coworker, and then finally there'd be only 1 book left for that last coworker. And multiplication principle would give us exactly the same thing, that we would have 120 ways to give away our books to those 5 people. Of course, if we remember to use factorials instead, that's a lot more efficient than relying on the multiplication principle. All right, second technique, permutations. This is used whenever we're thinking about arranging things, but also selecting things first. So I don't necessarily take all of my books and arrange them on a bookshelf. I take a few of my books and arrange those few on the bookshelf. So here, when we're talking about having a bunch of objects, n objects, and they're all distinct from each other, same as before, so same little restriction that was for factorials, they need to all be different. So we have a bunch of objects, and then I would like to select k of them and then put them into some sort of an order. That would be called a permutation. And the notation that we use for that is pnk. And pnk is a whole bunch of numbers multiplied together. It's n minus 1, n minus 2. It's a bunch of descending numbers all multiplied together, which really boils down to a factorial divided by a factorial. I'm going to point out that you don't need to care or remember this formula, so this is not really needed as a formula, because the reason you don't need the formula is because you have a function on your calculator. So you could write down, if you wanted to, in your notes what P and K means as far as an actual calculation. But I think the more important thing is to know how to compute it on your calculator. And for that, we also have a function for permutations, just like factorials. It's right above number 6. So if I wanted to compute P53, so if I had 5 books and I wanted to select 3 of them and then arrange them on a bookshelf, and I wanted to know how many ways there were to do that, that would be P53, and I would enter that as 5, second function 6. When I do that, that's when the P shows up in the little display window. And then 3, so my display window will say 5p3, and then I'll hit equals, and it'll tell me 60. Couple of little side notes about this. For P and K, N is the bigger number. That's how many objects we have. K is the how many we're selecting and then arranging. So for obvious reasons, K cannot be bigger than N. Something like P37 just literally doesn't make sense, because that would be saying you have 3 objects and you're going to select 7 of them and somehow put them into an order. That doesn't make sense, because how would you select 7 things if you only had 3 things to begin with? Same thing with the factorials. Even though maybe the question doesn't use the word arrangement, maybe you can think about things in terms of an arrangement. So we'll talk about that. One thing that's true for both factorials and for permutations, both of those are scenarios where there's some sort of an order that we care about. There's some sort of an order that matters. Sort of for obvious ones, if we're putting books on a shelf and putting them in an order, then obviously the order matters. We're going to look at cases where later on, what if we don't care about what order things are put in? What if we're not arranging stuff? We'll look at that a little bit later on. And we'll also look at how to tell, based on a question, whether order matters or not. All right, let's do some examples involving permutations. So I've got examples 3 and 4. Example 3, we've got 12 Olympic men's hockey teams, and I'm going to be giving out 3 medals, gold, silver, and bronze, and some assumptions we're making here. All the medals will be given out. We're not doing anything where nobody gets the gold. I'm also not doing any ties, so there's not going to be a tie for silver or anything of the sort. So I'm going to give out 3 medals to 3 different teams. So if we're thinking about this, I mean, what we're needing to do here is, out of the 12 Olympic men's hockey teams, there's going to be 3 winners. So there's 3 teams that need to be selected to be the winners. And once I know that, let's say, the winners are teams A, B, and C, then the question remains gold, silver, and bronze, whether it's A that's gold, or B that's gold, or C that's gold, and who gets silver and who gets bronze. In other words, we've got our little podium, we've got our gold, silver, and bronze to give away, and the question is, when these 3 teams go to line up, what order are they going to go in? Is the gold going to go to A, or is it going to B, or is it going to C? What order should these teams arrange themselves in when they go to line up on the podium to go get their medals? So really what we're doing, even though it doesn't mention arrangements in the question, we're taking, of the 12 hockey teams, we're selecting 3 of them to be winners, and then we're putting them into some sort of an order to decide who's getting first, second, and third place. So I could imagine this as a permutation. This is P12-3, that out of 12 teams, we're going to select and arrange 3 of them. So 1,320 ways. You might have also noticed me quickly writing down and then erasing this, the multiplication principle approach. I wanted to save that for a little bit later. We could tackle the same question just like with factorials. Anything that involves a factorial, you could have done it with multiplication principle. And same thing with permutations. A permutation could have just been done with multiplication principle. Because we could say we need to decide who's going to win gold, silver, and bronze. And at the beginning, there'd be 12 choices of team to win the gold medal. There'd be 11 choices left who could win silver, because once we've given the gold medal to a team, it's not going to win any other medals. And then once we've given away the gold and the silver, 2 out of the 12 teams have taken the medal. That means there's only 10 teams left for who could be getting the bronze. And again, gives us the same answer, 1,320. Same sort of an idea for 4. The question doesn't mention arrangements directly, but we could sort of imagine an arrangement. So I have my 4 different houseplants. I've got my houseplants 1, 2, 3, and 4, and then I've got all these windows. I'm going to label my windows A, B, C, D, E, F, and G. So those are my windows. So if I'm thinking about this, if I'm trying to place my plants in front of these windows and I want to make sure that every window has maybe one plant in front of it, maybe zero, so there's not going to be any doubling up. I need to, out of these 7 windows, I'm going to need to select 4 of them. So there will be a selection that happens. And then I need to decide which plant goes in which window. So in other words, I need to know what order do these plants go in. Is it plant 1 goes in window A, or is it plant 2, or is it plant 3, or is it plant 4? So even though the question doesn't mention putting things in an order, really what we're doing is I am taking my 7 windows and I am selecting 4 of them and I'm imagining putting them into some sort of an arrangement. Plant 1, does that go for the first, second, third, or fourth of my selected windows? So in other words, out of the 7 windows, I'm going to select and arrange 4 of them. There should be 840 ways for me to place my plants. The other way that you could do that, of course, is multiplication principle. You could say there's 4 tasks. You have your first plant, and your second one, and your third one, and your fourth one. And for your first plant, there would be 7 choices for the window, what window you might want to put it next to. And since we're not repeating a window, then that means for plant number 2, you would only have 6 choices of window. And then for plant 3, there'd only be 5 windows left available. And then for the last of my plants, there would only be 4 windows available. So either way, you would find that there's 840 possible options.